guys. How you doing? You awake? Oh my goodness. How many people have a hangover? Yay! So I'm Z, and I'm gonna talk to you guys today a little bit about how you can write computer programs that solve problems for you, or at least provide interesting observations into a program for you. If you'd like, you can tweet absurd things at me during the talk, and I will read them later and laugh and make fun of you. Or you can, just visit the website where I'll be putting these notes up later. So there's this idea of a learning funnel. We take things and knowledge and information, and it starts out kind of like a big old mystery, like, oh no, apparently my pen's not working. This is a travesty. I'll use my finger. So, oh, my finger's not working. How does that work? Oh, there it goes. Okay, good. Apparently my finger needed to touch something else before I could actually use it. So things start out as a mystery. Like, I don't know how to sail. I have no idea, you put me on a boat in a pond and it will sink because I'm really bad at sailing. I have no idea, the mechanics of it. But if you give me instruction and you work with me and you teach me about things, slowly I get to move knowledge about how to sail into the hunch space or the heuristic space. I start to have an understanding of what I need to do in order to actually make sailboat move in given direction. Maybe at this stage I still get blown wherever the wind takes me, but at least I don't sink every time I get on a boat anymore. And then, I continue to refine my hunches until I get to the point where it's just an algorithm. I'm like, okay, I can see by the color of the sea that this is where I want to be. And I didn't mean to rhyme, but it works, so it's all good, right? And as a person, we actually take knowledge and move it through this funnel. We go mystery, heuristic, or hunch, and then algorithm. We just know what we need to do. We understand it almost intuitively. We also do this as a society, right? So 800,000 years ago or whatever, we did not know how to sustain ourselves with food. It was just forage, forage, forage. That's the only way we survive. And then all of a sudden, agriculture, we're oh, I think if we put stuff in the ground, it comes back up and we can eat it later. And that just was mind-blowing, right? And it totally just changed the way civilization works. And as we refine these hunches, we get to the point where we've got Montezuma or whatever it's called, and I'm accidentally breathing into the microphone because it's so close to my face. And we've got these ability to create corn or wheat that's maybe 10,000, 1,000, 2,000 times more productive than just regular old wheat. There's other trade-offs there which I'm not going to go into. And so that's the learning funnel. It's this idea that knowledge moves from mystery to algorithm over time. And creativity is how we move along that funnel. Now, certain pieces of knowledge have different ramifications. So let's consider maybe a hamburger, the knowledge of how to make a hamburger. For me, it's the quality of a burger is not very good, but then it kind of goes up with time. And then I've got it maybe algorithmized, and then it kind of drops off a cliff here, because what happens is we over-algorithmize it and we lose everything. So this is McDonald's, right? McDonald's has algorithmized the burger. There is no joy, no fun, no nothing in the burger. It's just an algorithm, mix wheat plus meat substitute equal burger, right? Back here we have this, there's this great burger joint in Cleveland called Johnny's Little Bar, where they have somehow perfected the algorithm of making, not perfected the algorithm, but they've combined this algorithm of how to make a burger quickly with their hunches for what a good burger is like. And they always give me a different special burger of the day, and it's amazing. They feed hundreds of people at a time. It's insane how it all works. And then there's my dad, who's really good at doing a barbecue, right? And he's got some hunches, and maybe he's he can feed about 20 people at a time. The burgers are reasonably consistent, but it's always different, and he's just working mostly on intuition about when does he flip the burger, when does he add garlic salt, when does he put on the onions, all these things he's making different decisions on. And then there's me, and I don't cook it all the way through, or I totally forget to put on pepper. Making a good burger is a mystery to me. Eventually it'll be better. And so there's also things that have this diminishing return, right? So let's say you're learning another language. I went to Taiwan for 3 months, and I speak a very small bit of Chinese. Before I went to Taiwan, I spoke even less Chinese, and I was really here. I could maybe find the bus and I was basically at the mercy of whoever I was with. What English did they know? After a couple months, I kind of got to hear I can now order coffee. 請叫我一杯咖啡. And that's really about the extent of my knowledge. I can order food, I can order coffee, I can find the subway station, but it's good enough that I can actually get around. Like, my quality of life is a little bit better. There's people who've been studying Chinese for 3 or 4 years who really understand the language, and they're doing really well, and they can have conversations, and they're significantly better than I am. And then there's people who maybe done 10 years or 20 years, and their understanding of the Chinese language, it reaches a peak, and it doesn't increase in quality over time. So different things actually move through the knowledge funnel in different ways, and they have different quality ramifications or efficiency ramifications. There's also things like perhaps programming. With programming, as you increase your knowledge and as you build on your skills, you continue to see these huge leaps and bounds in your understanding. So when I first started programming, how do I put something to a screen? I have no idea. How do I put something to a screen? And then, okay, I could do that, yes. And that's not very exciting. It's not very effective. There's not a lot I can do with that. But as I continue to layer on information, I can make a website. I can make a website that reacts to people's doing things immediately. I can do this, I can do that. And now I can do concurrent multi-threaded systems across, sharded blah, blah, blah. MongoDB, web scale. And I can just keep on layering on information and knowledge until I just keep on increasing my quality and efficiency. And so that's one of the really powerful ideas of this knowledge funnel is if you invest in the things, moving them from question mark to hunch to algorithm that have these building returns. Maybe it's not exponential, maybe it's just a linear building. Every time you improve the algorithm, or every time you move it along further along the funnel, you get qualitative, quantitative, valuable returns. One last thing, and then we're going to start talking about computers, programming computers. There's this idea of risk management, and we all are kind of used to this. We're programmers, we get asked to make something, and we're told, hey, we need this by Wednesday. And you're like, okay, let me think. Yeah, I'm probably not going to get it by Wednesday. I can't get it by Wednesday. Maybe Friday? And they're like, no, it needs to be Wednesday. And then you're like, okay, fine. I'm just going to work, 20 hours a day for the next couple days, and I'll make sure I get it for Wednesday. And so our theory of risk management is either work harder or just collapse in a heap sobbing at the bottom of the stairs. Apologies. Did that go through the microphone at all? Yes. Mad skills. And so we can think of risk management as just taking points in time and then deciding how hard we're going to work in order to make it happen. In reality, risk management looks something like this. And hopefully there's enough contrast in this color. So let's pick red. There we go, red. And, oopsies, that's not the way I want to draw this line. Give me a second. There we go. All right. So risk management actually looks a lot like this. It's a cumulative S-curve, right? So if we're looking at Monday, we've got maybe let's get another color here. We've got maybe a 7% chance that we'll be done by Monday. Maybe it's a 35% chance we'll be done by Wednesday. And maybe a 90% will be done by Friday. But in reality, it's looking like it's going to go into next week. And so what you have to do is you have to go to your boss or whoever your client is and say, hey, here's what my risk curves looks like. I really don't think it'll be done by Friday. What can we do to mitigate this risk? And working harder is not mitigating risk. In my opinion, there are only 4 ways that we improve our chances. Thank you. Ash is my favorite. Sorry, Evan.
Still Iron Man.
You're still Iron Man? That's okay. You guys can fight for Iron Man. There's only 4 ways that we can actually mitigate risk, right? We can either eliminate functionality, eliminate parts of the requirements, eliminate the things that our clients want us to do. We can either innovate, which is where we call up, Johnny, what's his name? Johnny Ive? I almost called him Johnny 5, which would be awesome. But we call up Johnny Ive. We're like, hey, Johnny, how do I do this design better? And Johnny's like, oh, well, let me think. And then he goes off for 5 days, and he comes back from his retreat in the mountains. He's like, oh, you must make it mauve. And we're like, oh, thank you, Johnny. And everything is better. Or you can iterate. You can get something, you can put it in the world, you can try it out a little bit, and learn from that trial, and then build upon your next solution, right? And that's another way you can mitigate risk. Or you can actually collaborate, and you can say, okay, I know some of this, you know some of that, let's get together and make some peanut butter cups, right? Let's get some chocolate and peanut butter together and like collaborate in order to solve this problem, in order to solve this user story or whatever it is that our client wants us to do, or our boss. And what this does is it alters the S-curve. And it each mitigation strategy alters the S-curve in different ways. No, nope, that's not how I want to draw it. I'm bad at drawing, which is why this is an adventure. So can anyone see that little light blue line? Barely? Okay. So that's our base management curve, we're going to say. And if we eliminate some part of the complexity, or maybe some of the user requirements, or some of the technical interfaces that we have to deal with, we basically just shift the S-curve up like this, right? We can increase our probability by a certain amount because we've eliminated some of what's going on, and it just like since there's less to do, we wind up having less problems that we're going to encounter. Or we can oopsies, I need to remember which order I did these in. Innovate. No, not that one. There we go. All right. Or we can innovate, right? So we call up Johnny Ive, and Johnny is going to go off into his little bubble. And like he's gonna come back to us with the solution, right? And that's okay. And we don't really know where the solution is gonna come from, what it's going to be, and really how long it's gonna take Johnny. So it kind of looks like this. We're pretty sure he's gonna give us the solution, and generally he gets back to us in a week or so. So we think that it's gonna wind up that he's gonna have a solution to us by Friday because he's just a genius. And that's how a lot of freelancers operate. We're like, don't worry about it. We'll just take this. We'll just take this and we'll take all your problems away and make sure that they disappear, right? And those freelancers operate on this innovation risk management curve, where they don't give any feedback necessarily until whatever feature is requested is done. Or you can iterate. And when you iterate, generally what happens is you pay some upfront cost. You build something the entire way through, and it takes longer than just building a very small chunk and then layering it on. But what it does is it squishes the curve sort of like this. So that now you see on Wednesday, you've got closer to an 80%, 60, 70% chance of success as opposed to a 45%, right? And so by applying and layering these techniques in, you can alter your risk curve for delivering any feature over the week. Collaborate. Collaborate's the final one I want to talk about. Let's make it red. No, wait, I already used red. Let's make it orange.
Mauve.
Mauve? I don't think I have mauve. Oh, I got this pink. Oh no! What happened? No! I'm gonna make it green. Okay. And collaboration generally, well, let's redraw that. It has some upfront costs, but then you pretty quickly start building upon something. And so it actually, when you're pairing or when you're going just whiteboarding for a minute with the right person, you wind up being able to remove a lot of the risk. All right. So those are the 4 ways that I would recommend you approach risk management. And what does this have to do with computers programming themselves? You guys came here because you wanted to talk about machine learning. You're like, oh yeah, he's going to drop me some Bayesian algorithms on me, and it's going to be amazing. I'm going to go home, and I'm going to be like, yeah, now I understand some crazy-ass formula. And unfortunately, I'm not going to do that for you guys today because you can find that in a book. There's dozens of books upon machine learning that you can learn about, and all of them tell you the same thing. Really, there's 3 kinds of machine learning or specific intelligence algorithms, right? There's machine learning, which is really common. There's genetic programming, which is used in some situations. It's more around simulation and that kind of thing. And then there's generative programming, which was something that emerged in the 1980s and then got kicked in the shins until it disappeared. And I think it's on its way to come back, or I really hope it is. So machine learning is all about the algorithm. You write one algorithm, you get a bunch of training data, it stores the results, and then the algorithm also takes into account the results when it actually gives you a response. So what is that simple chatbot, that website you go to when you have a conversation with a robot?
Eliza.
Well, Eliza is, I think she might have also used machine learning, yeah. I'm thinking about the one it almost passed the Turing test 2 years ago.
Cleverbot.
Cleverbot, yes, that's the one. So Cleverbot uses this type of formula. They wrote an algorithm and they just said, I'm going to throw as much data as possible against it, and it's going to know which results are good or bad, and it's just going to continue to get input, check the results, send output. Like that's the way their algorithm works. And the way they scale that is they add a lot of databases, and they make sure that the data persistence layer is very, very fast. It can be read from really quickly, and it might be written to a little slowly, but it's just fast. Genetic programming is where you write some code that generates a series of algorithms. Generally, there's many of them. It then runs those algorithms against a scenario or a simulation. And it says, hey, algorithms, I want you to solve problem X. Like, I just want you to give me a solution. That's all it really cares about. And so it runs those algorithms against a scenario. It assesses them based upon how well they performed in that scenario. Maybe they did really, really well. Maybe they did really, really badly. And the ones that did really, really well, they generally take those and they alter them in some way. Maybe they do like breeding, where they mix solutions together, or maybe they do just a random mutation of the different algorithms or whatever, right? And then what they do is they rerun them against the scenario, and they do this over sometimes months at a time. It's very expensive. People buy giant clusters of machines. There's people who do this as a hobby wind up like having server rooms in their basement because they're like, oh, I just need more power. If only I had 1 teraflop more, I could solve this like maybe 15 seconds faster, and it'd be so worth it. And it's all about, in genetic programming, it's all about the speed of iteration, the processing power, how many algorithms can I be running concurrently, like all these things. These are the questions that genetic programmers are generally asking when they're trying to tune their genetic algorithm. Generative programmers generally work on much shorter cycles. What I wind up doing is I come up with a hypothesis about my entire experiment. So I'm using genetic programming right down here. I'm using that as an experiment, and I'm building out like, okay, I want to run a very simple experiment. I'm going to assess the results, and then I'm going to create a new hypothesis. And it's much closer to an iterative agile development process, because what's happening is I don't care if I just create 10 algorithms, that's cool for me. Because I'm not really looking at I don't need to be super statistically relevant. Like 100 algorithms is generally pretty good. I don't need 10,000 or 50,000. I'm not looking for an answer. I'm looking for surprise. I'm looking for something interesting about the way the computer goes about solving the problem, so that I can make a change to the simulation that I'm using, and then continue to evolve my hypothesis, evolve my experiments, and keep on analyzing the results. So what's the difference really? I mean, genetic algorithms we've already acknowledged are iterative. They repeat themselves. You know, they're building 10,000 different algorithms, and then they're assessing them, and they're iterating upon them. And it is truly an iterative process. It is generally a black box iterative process, but it is iterative, just like generative programming is. It is also innovative in the sense that we really have no idea what's going to come out or when it's going to come out, right? Like it's basically this black box. It's calling Johnny Ive and saying, hey Johnny, I really need you to design a wire for cell phones that's 10% more efficient. And Johnny goes into his cave, or in this case, the genetic programming algorithm goes into its cave and runs billions and billions of different ways to build a wire and design a wire, and winds up coming back with something that looks like it will work. And it does, because we're able to provide a good enough simulation. But it's not really collaborative. It's really totally black box type stuff. Like maybe I'm collaborating with different people, but the computer is the computer and I'm the programmer, and never the twain shall really meet. Like what happens a lot of the times is you'll do like whiteboarding and building out the simulation that you want to run, and you'll spend all your time making that simulation, like big upfront design to make sure the simulation is good, and then you're just like let the computer go, and like it's really bad in the sense that you don't really learn from it. And with generative programming, you're okay with mistakes, you're okay with failure, you're okay with errors, because what you're doing, you're not looking for an answer, you're looking for an interesting approach to the answer you're trying to get. You're looking for something that informs you. And so what you wind up doing with generative programming is creating a language that you and the computer both speak reasonably well, and you are running that against the simulations and analyzing the results, being like, okay, it looks like I've got, oopsies, don't fall asleep, thank you. You continue to, okay, yes. Sorry, you're building this language. The language is used to communicate between you and the computer. You can read what the computer tells you, and it can give you insights into the way that you're solving the problem or potential ideas for where the problem is solved. And the most important real difference between generative programming and genetic programming is genetic programming is seeking answers. Like, I need a 10% improvement in my engine output, or in my whatever. Like, I need to design something that can move quickly across the landscape, or any number of things, right? That's what genetic programming is generally about. And generative programming is more about taking small steps, relaxing, refreshing, just kind of thinking about it, saying, okay, that's interesting. Apparently, if we do this, we rotate, let's say we rotate this document image 35 degrees this way, for some reason, the OCR read rate is higher. I don't know why that is, but that's what's happening. And so then you can dive in and start to understand, like, okay, what's happening? Oh, it's because of the way, like, that maybe the light just travels across the page, or any number of things, right? You can actually begin to attempt to understand the problem as opposed to just hands off, hope the computer gets it right, and then walk away, right? So let's get back to the knowledge funnel, right? In my opinion, and I'm a hobbyist. No one's paying me to do this kind of thing. I find it very interesting. I find it very enjoyable. But I'm not a professional genetic algorithm creator. In my opinion, though, genetic programming is for here. When you've already decided that this is an algorithm we want to tweak. We want to get more gains from this. Like, we want to increase performance of MySQL's lookup searches or indexing or something like that, right? And so you might be like, okay, I can't think of a way as a human. I'm going to have the computer do it for me and have it iterate upon it very, very quickly. Generative programming is for here. How do I build a self-driving car? I don't know. Like, I can try it. I can simulate that reasonably well. And so I can kind of like, I can do this iterative approach to developing the algorithm. And I can use that to move my knowledge of how to build a self-driving car from mystery to hunch. And I can then, maybe I have to spend some time as a person, like understanding the hunches that I have before I can begin to move it to algorithm, right? And so that's, I believe, the main difference between what generative programming is for and genetic programming is for. And professionals may disagree with me here, so don't take anything I'm saying like with that in regard to gold, but I think it's really important. And let's get back to this lovely risk management curve, right? So the main difference now is that genetic programming and generative programming both seem to take years. It's mostly done in academia or for research projects from like the Department of Defense or anything interesting and fun like that, where you design better, faster ways to kill other people, which is the point of technology, right? To kill other people, and it's all about like taking a long time to get to an answer from a mystery or from something that we want to improve an algorithm for. I keep making a joke that I'm Walter White because I've had this cough for like 3 weeks now, and I'm just waiting to start learning how to cook meth, and I'm going to use my genetic algorithms to teach me how to cook meth.
What are you waiting for?
What am I waiting for? You know what? I live in Michigan, so I don't need to wait. No, seriously. Like, there's 2 houses burned down every year in my hometown because a meth lab just gets out of control. It's pretty amazing. I could just get excess stuff from them. Corner of the market. Anyway. Oh yeah. This risk management curve. Risk management. So if we look at our initial curve, like let's say self-driving cars. Oh, there's my color that I wanted to use. It's something that maybe it looks like that, or maybe it looks more like, okay, it's more likely, okay, we're looking at maybe 63% at the end of year 3 that will have a prototype that'll work. And I don't know how long we'll live. I really don't. But this is a long period of time. It's non-trivial periods of time. And so applying risk management is even more important in these longer periods of time. So they could eliminate requirements. Oh, we don't care about safety. That's not going to work. They're never going to get anything. That's not going to work now. Or they could think about, how do we innovate in this? And they can write a genetic algorithm that just goes and goes and goes and applies. And then maybe that'll increase their probability that they'll finish in the middle of year 3 as opposed to like year 7. Or they can be like, okay, we're going to get some of the leading experts in artificial intelligence and automotive design and like a bunch of different places, and we're going to collaborate together. And that's going to look like this. So that, like, well, that's going to look more like this, let's say. Or they can say, like, we're going to do something where we iterate upon a very basic design, and it's going to shrink our curve a little bit, and we're going to look maybe more like that. And so they can choose each of these things, and or they could simply start to use some generative programming techniques, like start up a side project. We're like, okay, we're going to pay you 3 people lots and lots of money to sit in a room and build, working with a computer that acts as your virtual lab assistants, and use generative programming to approach this self-driving car problem. Build out a simulation, iterate upon your initial design, like iterate upon the algorithm that's used to build the algorithms, improve how you assess the algorithms, like just continue to tweak and play with until you wind up with a good algorithm for maybe changing lanes with safely, right? Or then, okay, maybe layer on top of that, it not only can change lanes safely, but maybe it can also merge onto a highway safely, and give it very small, specific problems, run it against thousands of simulations over time, and look at like why is the algorithm working well? Oh, the one that changes lanes safely actually turns on its blinker 55 seconds before any of the other algorithms, and we never would have thought of that. We've been like, oh, just turn the blinker on and it'll be fine, right? No, it's actually about timing of when you turn the blinker on. And so if you have a good language, if you have a good DSL, then you can wind up understanding like why this algorithm is better, that algorithm is better. And that's what I would really recommend Google does. If they'd like to pay me lots of money to sit in a room and do this, I would be happy to. It's super fun. I do it. But yeah, anyway. Why Ruby? That's the last thing I want to talk about. So Ruby is a language that is built upon community. It's already got this idea of iterative development, test-driven development, right? You guys write scenarios every single day, maybe using RSpec or test unit or mini test or even Cucumber if you want to shoot yourself in the foot. And sorry, was that controversial? Okay, good. And so you're writing scenarios every day. You're assessing your code to determine, is this code up to snuff for these scenarios? So you're already like naturally attuned to the idea of I write code, I assess the code. And you're also used to writing languages. You guys write DSLs for everything. Like, I'm going to shove something on the internet. Well, I can't just write a function for that. I need a DSL for shoving stuff on the internet. Like, it's almost absurd how much DSLs we write as Ruby programmers. It's absurd. And so those 3 things in combination mean that you guys are poised. Like, if you guys can get into the idea and understand, like, how do I write code that writes code? Like, if you can bridge that gap, you will be able to augment your intelligence. You'll be able to, I don't call it cognitive augmentation. A guy named Andy something does, whose name I can't remember, will say you can augment your intelligence with this new technique or this tool. It's not a big tool, not a lot of writings on it. There's not a lot of like really good information on how to do this well. But if you start with the Rubyisms, the testing, the scenarios, all that kind of things, and then you move to the genetic programming side, like how do I write algorithms that write algorithms, how do I assess those algorithms, like how do I mutate those algorithms, and really dig deep into there, and then marry the 2 ideas together, iterative design and genetic programming, then you are going to be able to tackle problems you have never understood before. And that is really what this is about. This is about being able to tackle problems that we can't understand and actually begin to solve them by virtue of working with 1,000 electronic lab assistants. And yeah, that's why Ruby. Let's see, there's something else I wanted to talk about. Oops. I'm so glad I don't have a password on this right now. I like took it off because I was afraid I'd fall asleep, and then you guys would know my password. But anyway, oh yeah, I'll talk to you about the language that I built. So I wanted to write a genetic Sudoku solver, and I wrote a language called Shift. And all Shift is good at is working with grids of numbers or grids of things, determining the probability of what one of those cells on the grid should be, and then returning the values that it decides the cells should have. And that's all it does, right? It's a very simple programming language. It's non-Turing complete. It doesn't loop. It doesn't have any function calling yet. But as I evolve the language, it will get better at solving the problem. And hopefully I'll wind up with a very interesting solution to how we can solve Sudoku by simply rotating and applying transformations to grids. And if you don't understand how that works, I didn't either for the first 3 weeks. But the language still kind of works and is still under evolution. Thank you for your attention. I'm sorry if I talked really fast or rambled. I still have like 4 slides to go. Oh yeah, if you want to see any of the genetic stuff I've got going, or the generative stuff I've got going, a couple of my old initial prototypes are on GitHub. Eventually, I will put new stuff up there. So thank you.